Oh, that was loud. Okay. I decided I was going to record this one because y'all get the benefit of me having done this a couple of times, and there's some things that I've realized that I forgot to add once people got started working on the homework. This is a short lesson. We're starting a unit on probability. Probability of rolling a 3 on a die, that type of thing. So today is just the basic probabilities. And of course, probability of an event. If I had, let's say I was flipping a coin, and we know what should be the probability of getting a heads? 50%. But if I just toss the coin 10 times, am I going to truly get 5 heads and 5 tails? But am I probably going to? Now, what if I did it over and over and over like a million times?
You're probably 500,000.
It's going to get a lot closer. So that is called the law of large numbers. It says as a probability experiment is repeated over and over and over, then the proportion of times that a given event occurs approaches its true probability. Now, just a wording, this pops up in the homework, and I forgot to put it in the notes when I edited them. Empirical method pops up in the homework, and all that says is that if an experiment is repeated over and over and over and over, you can use that data to estimate the true probability. So it's kind of like the law of large numbers, just worded a little differently. It's saying if I do flip a coin a million times, I can use the data from that experiment to estimate the true probability of getting a heads on a coin, because it's going to be closer to the truth. So when you see empirical method pop up on the homework, it just means use the data from the test. Don't just say, oh, it should be 50-50. Use whatever data they give you. All right. Now, before we can actually find probability of things, we need to know the sample space. And that's all the possible outcomes of an experiment. It means to list all the possible outcomes. So tossing a coin.
1, 2, 3.
List all the possible outcomes. What are my possible? Heads or tails. That's what we're talking about. Okay. Rolling of a dice. 1, 2. Well, we're talking when they say dice, they're usually meaning 6-sided.
Yeah.
If they meant 20-sided, they would actually say it. Now, roll of 2 dice. Here's where I made a mistake in first period. We were like, oh, let's just kind of think through it. And we didn't write it all out. There's a later question that asks about rolling of 2 die. And it's a lot better if you have your sample space drawn out. So, right, but we need to list them. Okay, so I could have a 1 and a 1. A 1 on the first one and 2 on the second one. 1 then 3, 1 then 4, 1 then 5, 1 then 6. Or 2 and 1, 2 and 2. So on some of the homeworks, it'll actually tell you, hint, draw out your sample space. This is what it's meaning to do. Sometimes this really does help you find your possibilities. I've seen some questions where it asks about the sum of 2 dice that are being rolled. If you didn't list them all out, you wouldn't know what they would add to be. So it really does help. 4 and 3, 4 and 4. 5 and 2, 5 and 3, 5 and 5, 5 and 6. And y'all already said it. How many options do I get? 36. A quick way to know that is we get 6 options on the first die, 6 options on the second one. 6 times 6 is 36. All right. What about if we're selecting a student at random from a list of 10,000 at a university? What's my sample space? All 10,000 students. If I actually knew their names, I'd write them all out. Now, sometimes you can use what is called a tree diagram to visualize a sample space. These are also used to find probabilities later on in the unit. So this is kind of our introduction to tree diagrams. So let's say we have that women's purses are made in blue, yellow, or white, and they either have silver lining or black lining on the inside. So if we draw out our possibilities, we have 3 possibilities for color. So this is what a tree diagram kind of looks like. You list out your possibilities. Now, can I branch off of these? So if it's a blue purse, we have 2 options for lining. So if it's a blue purse, it could either have silver lining or black. Then if it's a yellow purse, it could either have silver or black. And then if it's white, silver or black. So when we're reading these, it's kind of like you have to go down the branches. So you follow the path, blue, then silver, or yellow, then black. And we'll be reading those to find probabilities later on. But right now, we're just using it to visualize all the possibilities. So what's my total number of possibilities? 6 possible outcomes. The easy way to find your possible outcomes, we had color and then the lining. How many colors do we have?
3.
How many linings? 3 times 2 is 6. So there's the shortcut for finding your number of possible outcomes. Now, when we talk about events in probability, that's the outcome or collection of outcomes from a sample space. So part of that sample space. A probability model for an experiment consists of the sample space along with a probability for each, this should say event. When we talk about the probability of an event, this is the notation we use. So probability of A happening. The way we find that is we take the number of outcomes of event A divided by the number of total possible outcomes. All right, so we're going to practice that a little bit, either from wording, from some of our stuff that we already wrote out, or from tables as well. So that's all we're doing today. Can I flip the page yet? And I'll get you that first page. Not that it's really going to be necessary. Find the probability of each. An odd number comes up when a fair dice is rolled. What do they mean by fair dice? The fair part means that it's not loaded. It's got an equal opportunity for each number.
Oh.
Some people, it just means that it's fair. There's nothing wrong with it. There's not an edge chipped off. It's perfectly good die. So what's the probability of getting an odd? How many odd numbers are there? 3 out of the total 6. Now you can reduce the fractions, or you can write it as a decimal. Any of those 3 ways are fine, and they'll show up as either fractions or decimals on the homework. Now, what about the probability of the same number on both when 2 dice are rolled? This is when it was helpful to have that drawing wrote out. So the same numbers on both. How many were there? 6 out of 36. We always start with the full one. There's 6 possibilities. That's 1 out of 6. What about getting both odd? So if we flip over Both odd, not on every row. Because the row that had the twos first, they wouldn't both be odd. Three, three, and three, five, five, and five. So there are 9 ways out of 36. Very good. Which would be 1/4 or 0.25 or however you want to write it. Now, some of the rules about probability is that the probability of an event is always going to be between 0 and 1. In other words, if we wrote it mathematically, the probability of event A would be between 0 and 1. So 0 is less than or equal to the probability, which is less than or equal to 1. Now, why do we say or equal to 1 and 0? So if A cannot occur at all, so the probability of that happening would be 0. Like the probability of rolling 7 on a dice. Can you roll a 7 on a 6-sided die? No. So the probability of that happening is 0. What if we know it's certain to happen? It would be a full 1. So knowing it'll never happen, the probability is 0. Sure thing it's going to happen, like saying, if I roll this dice, I'm going to roll a number between 1 through 6. The probability of that happening is 1, 6 out of 6. All right. In the Georgia Cash 4 lottery, a winning number between 0000 and 9999 is chosen at random, with all the possible numbers being equally likely. What is the probability that all 4 digits are the same? So let's think about the ways we could have all 4 the same. 0000. Nope. So that's why I'm writing them out, because a lot of people think there's 9 ways this can happen. But if we write out all the ways it can happen, if we count that 000, that's 10. So the probability of all 4 the same, there's 10 ways that all 4 digits are the same. Now we need to know the total possible number of outcomes. How'd you do that? Solving them together? Yeah, because if you go from 1 to 99999, then you add in that 0000, that is 10,000. The other way to think about it is that first digit could be 0, 1, 2, 3, all the way up to 9. So there's 10 possibilities for the first digit. How many possibilities for the second one? 10. 10 times 10. 10 times 10 times 10 times 10 is also 10,000. So that's another way to have thought of it. I'm just showing different ways. And you could reduce the fraction or leave it. Now, anytime we're sampling from a population, when we're doing a simple random sample or one of our other methods, we're actually doing a probability experiment. The population is the sample space, and the members of the population are equally likely outcomes. So each member is an outcome. So let's say there's 10,000 families in a certain town, and we've categorized them. I'm sorry, Word decided it wanted to separate apartment into 3 rows. Probability that a sampled family owns a house. Owns house. So how many ways could we find a person that owns a house? Okay, so how many people own a house? 4,000. Out of our possible 10,000. Now notice the difference on the wording on the next one. It says the probability that the sampled family rents. Did it say rents a house? Rents an apartment? No, I just said the word rents. So if it's talking about just the number who rent, that's both of those together. Okay, I'm gonna show that I'm adding them together, but that's 3769. Okay, thank you. Good so far? The last thing we're going to talk about is what makes an event unusual. An unusual event is one that is not likely to happen. That means its probability is going to be small, but we need to have a rule of what small means. How small is small? So the rule of thumb, our cutoff number, our cutoff value is 0.05. So if I found the probability of event A and it was some number less than that, then we would say A is unusual. So if your probability is less than 0.05, that makes it an unusual event. So let's say we have a college of 5,000 students, 150 are math majors. A student is selected at random and turns out to be a math major. Would we call that an unusual event? Well, we don't know unless we find out the probability. So how many people were math majors? Out of, can somebody do us a favor of dividing 150 by 5,000? What is it? What was it?
Mine ended up being like 0.003.
I got
Maybe I'm way off. I probably wrote
0.03.
it in wrong.
Yeah.
50,000, that would be insane.
Yeah, I got 0.03. So does that make this an unusual event?
Yeah.
That's all we're doing today. We will do 5.2 in a moment. That's unusual.